we will use Python to apply PCA on a certain data set, and then we will apply a supervised learning algorithm such as support vector machine on the same dataset and measure the accuracy. So in the first cell, let's go over the code and see an example where we apply the PCA and see how we can get the parameters, as well as see somewhat of what we covered in the class itself. So in the first cell, what we have done at the top is importing a few packages and libraries. Some of these packages and libraries we will be using later on for instance, splitting the data, plotting some of the information, and the most important one that we need is the sklearn decomposition, which have the PCA algorithm already implemented for us. We started by setting a random seed from NumPy, so you can just set it to be 5 or any other value. And if you remember, we set this random seed just to make sure that we can replicate our experiment at different time. Then we loaded our data. So the dataset that we will use is the iris data that we used previously with support vector machine example. This iris data includes 4 different classes, and we have data and we have the target. So it includes 4 different variables, and we have 4 different classes within this data. The target in here is the label, and the data, or the iris.data, is the data itself. In the last line in here, I try to display the last or the first 10 rows from our data. As you see in here, it includes 4 different columns, and the data is not scaled. Initially, what we started by scaling our data and removing the mean. And if you remember from the lecture, when we talked about PCA, in PCA it's highly recommended, or we need to remove in fact the mean, or set the mean to be 0, or the mean of our data to be 0. So therefore, the first part, the highlighted part in here, it will remove the mean and set it to 0 for our data. And optionally, you can divide by the standard deviation to scale the data if you would like to scale it and just make it on similar ranges. And after that, in the last line within cell 2, I try to print the last or the top 10 rows just to see how our data looks like after it has been scaled. So I scale the data, I remove the mean first, and then I scaled it by dividing by the standard deviation. And you can see in here the x variable in fact is a NumPy array. So therefore I'm using the dot standard deviation, and I'm providing the axis. If I do not provide the axis equals 0, it will find the standard deviation for all of the values as if they are one matrix. Now we normalize the data, we remove the mean, and let's try to plot the relationship between every 2 variables. So within our dataset, remember that we have 4 variables, so we plot the 4 variables and the relationship between the first one and all other variables. So you can see in here the first one is between the variable and itself, and the rest are the variable and the other 3 variables, and so on for the rest of the variables. So what I've done in here, I converted the data frame, or I converted the NumPy in fact. So x normalized is the NumPy array. I converted this to pandas by using pd.dataframe, and then saved it in train stats. Then I used from Seaborn SNS a pair plot, which is a function that takes the dataset, and then we plot the relationship between every 2 or every pair of variables. So you can see in here, I'm plotting the relationship between the actual values of the variables. Unlike in the past, I used to plot the relationship between the parameters of the variables. So both are correct, and you can either print the relationship between the statistics of each variables, or you can print them between the variables themselves. So you can find sort of a relationship between the variables themselves. Then we started by calculating the PCA, and calculating the PCA and plotting a 3D shape. So if you see in here, I started with a figure just to plot the data after I create it, and then I created a sort of a rectangle. Just these are plotting functions just to plot my output. So you just put the plot functions together and just add a comment in here that says plot settings and configurations, just to display it neat, and as we will see it below. Then the next few lines, this is applying the principal component analysis on our data, and we start applying the PCA by calling the object decomposition that we imported from sklearn. At the above, if you look at all the way at the top, you will see that we imported decomposition from sklearn. Then from decomposition, I call the .pca, which will call our function, and then you can pass list of parameters. One of the parameters is the number of components. So in my case, I would like to reduce the number of parameters from or the number of components, sorry, from 4 up to 3 components. So I created the configuration and the settings for the PCA in this line, and that included the number of components. Then I fit the PCA on the overall dataset, or the dataset that you would like to extract the PCA parameters, or the uReduce, if you remember the uReduce from. And typically, this example on this line, you'll be fitting your data on the training dataset. So you'll take just the train split of the dataset and fit the PCA on that portion. Now, Z now will include, or the PCA, you can use either the Z or the PCA as the list of parameters. After I fit the PCA on the training dataset, and remember the X normalized does not have, or X normalized does not have the labels. Now I fit the PCA and I extracted the parameters, and in the next line I take these parameters and apply them on the X normalized split of the data, and this will create or produce the PCA data for us. Then I use the for loop in here, and this for loop will take every single variable within our data after I apply the PCA on it and plot it for me, just to show me how the plot will be in a 3D array, or in 3D shape, and this will plot it in a 3D shape, and then we will select a few of the variables and reorder them so they appear as you see it down here. So this is how we plot it if it's a 3D, and now PCA can be used not just to speed up the process of supervised learning, it can be used also to for visualization purposes. So now I can see how the data is distributed within my within the 3D plane. Now remember the variance retention, or how much of the variance you would like to retain. Like for instance, you decide you wanted to apply PCA and reduce the dimensionality and maintain or retain, like for instance, 90% of the variance of the original data. So let's see how we can calculate that, and how much data or how many dimensions we should retain for or should keep or use for the number of components, and determine the value of k, which k is equals to the number of components that you would like to keep, and what's the relationship between that, and how we can find the variance percentage that's retained. In this example, what I've done, I applied a PCA, and I applied it with the number of components equals 4, which is exactly the same number of components that I have within, or the number of columns that I have within my dataset. So the number of components, the maximum value will equals to the number of columns, or number of features, or number of variables within the given dataset. You cannot bypass that or exceed that amount. Like in my example in here, I have 4 columns in the dataset, so the maximum number of components I can use is n equals, or n underscore number of components equals 4 at most. So if you use the same number of components equals the same number of variables, then you are not applying any dimensionality reduction. I applied this and I used number of components equals 4, so I can show you now if I keep, for instance, all of the 4 variables, how much is the percentage of variance that will be returned. And if I keep 3 variables out of 4, how much is the variance percentage that's returned in these 3 variables, and so on until we see how much is the variance that's retained if we keep only one variable. So I fit my data, or I started by creating the configuration for my PCA using 4 components, and then I fit the model on my data uh, to find out what are the U reduce or the list of parameters that I will use to apply PCA. In the next line in here, we use the function, and this function called explained underscore variance underscore ratio underscore. And this variance ratio is a function that will display the ratio of the variance that's retained by each variable. Then I use cumulative sum just to find the cumulative sum for these variances. And then I printed the value of the variance retention or retained ratio, which will be an array. And this array will include list of ratios. So if you see the first ratio in here, the first entry is corresponding if we keep only one or use one component. If I use only one component out of the 4, then I will have 72% of the variance will be retained. If we keep only 2 components, 95.8% of the variance will be retained within my dataset. If we use 3 components, as you see in here, 99.4% of the variance will be retained within the data. So you can see in here, and if I use all of the 4 components, 100% or 1.0, which is equivalent to 100% of the variance will be retained in our data. So as if it's exactly keeping and retaining all of the data points. Now, I tried to print them in 4 different sentences, so you can see how, or 4 different lines. So you can see, for instance, if you would like to see what will be the percentage, the variance percentage that's retained in here if we keep only one k equals 1, or the number of components equals 1, that will be saved in variance retained ratio 0. And 1, or variance retained ratio 1, will be corresponding to keeping 3, and so on and so forth. So now you can look at this sentence or this array and decide how much is the percentage of variance that you would like to retain. Like, for instance, if you would like to retain at least 99%, so in this scenario we will pick k equals 3. So what I would like to do in here, I would like to keep k equals 3 because I would like to retain 99% of the variance of our data. So in the following example, I will use k equals 3 in the following examples. Okay, so now remember that one main component that when we calculated PCA was the covariance matrix, and the covariance matrix, it equals to n by n, or it's a matrix of size or belongs to R of n by n. And you can in fact retrieve this covariance matrix if you would like to use it by calling PCA. After you fit your PCA, you can call it by calling PCA dot get variance, and this will provide you with a big sigma. And then you can print it. You can use it as 2D matrix 4 of 4, which is n by n. The size will be n by n. The last thing before I start using the PCA, let me just talk about how to reconstruct your data. For instance, if you used PCA with 3 components out of 4, 3 components, and this will compress your data, reduce the dimensionality. Can I decompress it and retrieve it back? So yes, we can. Within Python there is a function within PCA to retrieve your data and put it to its original form, and this function is called inverse transform. Let's see how we can apply that. So what I started in here with, I created the configuration for PCA using decomposition.pca, and I decided to use the number of component equals 4. Equals 3. Then in the next line I fit the data set that I have on that PCA, and finally I transformed or converted the dataset, or compressed the dataset, or applied the PCA on the dataset that I have, and now XPCA will include a version of the variable X, and this version is the compressed version of the original data and the reduced version of that data. As you see it in here, I tried to print the shape, and the data is 150 by 3. So this is before, in fact. Let me just correct this one. So this is before applying the PCA. Now after I applied, so this is after the PCA, and after the PCA it was 3. Now what I would like to do in here, I would like to revert, decompress the data. So the function is pca.inverse transform, and then I provided the xpca, which is the values that I have compressed, and the reconstructed x is the value that was restored. So let's just call it a reconstructed. So the data that has been reconstructed, or the reconstructed data from PCA reduction. So now after I restored the data, as you see it in here, the dimensions are back to 150 by 4. So we have 4 columns, and the same data points that we have are 150 data points in the dataset, or 150 examples. Now let's try to see a complete example where we split our data into 3 portions, or 3 splits: train, cross-validation, and test. And then we take the train split, we use the parameters for scaling the data and extract them from the train split, and then we apply the same parameters on the cross-validation and the test. Then to apply PCA, we will use just the training dataset to extract the PCA, or extract the PCA parameters, and then we use these parameters to reduce the dimensionality of the cross-validation as well as the testing dataset. After that, we will train a support vector machine or any supervised learning model and see how and fit that model on the reduced data or the compressed data after applying the PCA, and see how the accuracy on both the validation dataset and the testing dataset. So this is a complete experiment using PCA and a supervised learning such as support vector machine. So we would like to use the same iris dataset that we have seen before, and we would like to reduce the dimensionality from 4 to 3. So we will keep the PCA component, or the number of PCA components, to be 3, because I would like to retain 99% of the variance within my data. And remember, previously we have seen that to retain 99% we need to keep 3 components. And feel free to repeat that step in here if you would like to see see how much of the variance you will be retaining. So now we started by retrieving the iris data set again. So I just retrieve a fresh copy, and my plan is to split the data into 60% for training, 20% for cross-validation, and 20% for testing. Now the dataset is in the form of a NumPy, so it's easier for me to deal with it as a pandas. So therefore I decided to convert it as pandas, and I use this line to convert it to be pandas data frame, which is pd.dataframe equals, this is the data, it will be the concatenation. So I use numpy.c underscore, which is a concatenation function that concatenate the data as well as the target, and remember that the target is the labels. The columns, I use feature names and target to be the column names for my data. Now the iris data frame, it's a pandas data frame that contains all of our data, or the data that we have within the iris data. Now let's start splitting the data. I split the data first for 40% for the temp and 60 for training, and then I use the temp and split it into 50-50, so it will be the test and the validation. And you can see in here, or remember that within this each dataset, well, we have the label or the target. So I tried to display the sizes of the data after I split it. So if you look down here, you will see that the dataset dimensions are 90 and 30 by 30, and the columns or the number of columns equals 5 because we do have the labels within the data. We removed and saved the labels of the data using the pop function and saved it in train labels, test labels, and cross-validation labels, or validate or valid labels. Then we use the training dataset or the train split. So this is the train split of the data to normalize the data by subtracting the mean and dividing by the standard deviation. And then we called it, I used the same parameters for uh, all of the splits. So I used the train dataset mean for normalizing the training dataset, normalizing the split, the test split, and normalizing the cross-validation split as well. In the following line, which is applying PCA, we created the configuration for the PCA by calling decomposition.pca, and we provided the number of components, and we would like, as you remember, we said we would like to reduce the dimensionality from 4 to 3 and retain 90% of the variance within our data, or 99%, sorry. Then what I've done in here, which is the one of the most important parts, I fit the PCA on the normalized train dataset. So I just fit the PCA on the normalized training dataset. So we did not fit it on all of the dataset. We just used the train split to fit the PCA, and this will extract the list of PCA parameters such as the U-reduce that we can use later on for normalizing everything else. Now, after we fit or extract the parameters from the normalization or from the training dataset, we will use these parameters to reduce the dimensionality for the 3 splits. So we'll use the same parameters in here by using PCA transform, normalized data, and this will reduce the dimensionality of the training dataset using the training parameters, and save it in norm train data underscore PCA. We have done the same for the testing dataset, and we used the PCA object that we declared in here, which includes the list of parameters that we extracted from the training dataset, and used it to transform on dimensionality reduction of the testing dataset as well as the validation split of the dataset. Then within this line, we printed the dimensionality or the dimensions of the data to see what's the results. So you can see in here the dimensions now are reduced. They are 3 and 3 and 3. They are 3 because we reduced the dimensionality from 4 to 3, and remember that this 5 includes the labels. This one does not include the labels, so therefore it's 3. The labels are in a different object. We extracted that or removed that at this lines or these lines. Now we would like to train a support vector machine. So at the top, if you look at the libraries and the package that we imported, I already imported the support vector machine from sklearn. So I called a support vector machine with .svc. I used a regularization parameter of c equals 1, and I used the kernel, the sigmoid kernel. So you can use any of these kernels and experiment with it and use the cross validation to determine which kernel is the best and which set or combination of parameters are the best. So it's not the objective of this video, so therefore I will just use very simple parameters and proceed with that. Feel free to go and play with the parameters and see which combination of the parameters will provide you with the best results. Then I fit my support vector machine on the training dataset with the labels. And remember that this train dataset is the PCA or the dataset after I applied principal component analysis, and I retained or kept only 3 components or 3 variables. After that, I applied predict on the testing dataset, and I measured the accuracy and compared the predicted labels with the actual labels for the the test data set, and I reported the accuracy from matrix.accuracy score. Similarly, I've done the same for the validation, and it looks like the accuracy for both the test dataset is 90% and the cross validation produced a 90% of accuracy. So this is a complete pipeline and quick tutorial, in fact a detailed tutorial on how we apply PCA. And as you see in here, PCA is already implemented for us in sklearn. So all of what we needed to do, just import it and start using it by determining and deciding the list of hyperparameters. And we already talked about how to decide the hyperparameters and such as the number of components and how much is the percentage of variance that we would like to retain. And then I try to explain in details how you can use or divide your data into split, cross-validation, and test splits, 3 splits, and use the train split to fit your PCA parameters, and then use the fitted parameters or the parameters that you extracted from the train dataset and use them to apply dimensionality reduction on the test split as well as the validation split. After that, we applied a direct support vector machine, a supervised learning algorithm on the data after we split it. So feel free to apply neural network, logistic regression, or any other support, or any other supervised learning algorithm or classification algorithm on the data that you have, and it should be similar to how we applied the support vector machine. Thank you.